Hello, I am Flash Isaac and you are welcome to my physics class. Today, I shall be taking you through waves. Waves. I promise to make this class as simple as possible, as detailed as possible, and as interesting as possible. There shall be no stone left unturned so long waves are concerned. This is why you need to take a bottle of chilled water, relax, while we begin the journey. Without wasting much time, waves. Waves. What is a wave? Or what are waves? A wave is a disturbance that transfers energy through matter or space without transfer of particles. A wave is a disturbance or oscillation or vibrations or shakings. And this disturbance transfers energy. What is energy? Energy is simply antimatter. Look at this. Physics is the study of matter in relation to energy. Physics is the study of matter in relation to energy. Now, the universe is made up of matter and energy. Matter is anything that has mass and occupies space. Energy, on the other hand, is a property of matter. It does not have mass, which means energy is not matter. This wave or waves, they are disturbance that transfer energy. What does that mean? Since energy they don't possess mass, it simply means that it doesn't transfer mass. It simply transfers energy. It doesn't transfer matter. It transfers antimatter from one point to another. Now, this energy can be transferred through matter or space without transfer of particles. Wow! Now, this definition of waves is not something you just cram, or it's not something you just know to pass an exam. When you understand each of the terms, it becomes very, very interesting. Look at it. A wave is a disturbance. So, disturbance, shakings, or oscillations that transfer energy. Now, I've been able to explain matter and energy. When matter has to do with mass, right, or medium or material. Meanwhile, energy has to do with a situation where there is no mass, just a property of matter. So this disturbance transfer energy, and the opposite of energy is what? Matter or mass. It doesn't transfer mass, it only transfers energy, and this energy can be transferred through matter or space without transfer of particles. Look at something. Through matter or space, which means in the process of transferring this energy, we may need matter. On the other hand, we may not need matter. This takes us to types of waves or classification of waves. There are waves that need matter to transfer energy. In that case, we say that these waves, they need material medium. There are also waves that don't need matter to transfer energy. They need only space. In that case, we say that these waves, they do not require material medium. And as this wave transfer energy, they don't transfer particles. If a wave transfers energy through matter, that waves requires a material medium, because matter is material, is a medium, is a mass. We refer to that wave as mechanical wave. Mechanical waves are waves that require matter to propagate or to transfer energy. They require a material medium. Example, sound waves. Stadium wave or splinky waves. Now, Sound cannot travel without material medium or without matter. Sound needs matter. Sound needs air to travel. Sound needs metal or material. Let's say steel. Sound needs non-metal. So materials, when you hit here, you produce sound. As I'm talking now, you are able to hear me because of air. So sound needs all these material mediums to travel. Sound cannot travel in space or in vacuum. So when you remove air, anytime I talk, you won't be able to hear me because sound is not getting a medium to travel. And on the other hand, we have waves that don't require matter or a material medium. They are referred to as electromagnetic waves. These waves, they don't need air or matter to travel, or maybe mechanical waves like water waves that need water to transfer energy. No, these ones, they are electromagnetic waves. They travel in electromagnetic fields. So examples of electromagnetic waves are, this is the shortcut, ga, gazulia, gamma rays. In my radioactivity video, I explained that radioactivity is the spontaneous disintegration of the nucleus of an element to emit radiations. And these radiations emitted are alpha particles, beta particles, and gamma rays. Alpha particles are helium nuclei. Beta particles are fast-moving electrons. But gamma rays, on the other hand, they are rays, they are radiations, they are electromagnetic radiation, they are energy. So gamma rays, these are waves that travel without matter. They can travel in space. They don't really need a physical medium or material medium to propagate. X-rays, ultraviolet rays, light rays or light waves, infrared waves, and radio waves, these are electromagnetic waves when they transfer energy through space. In other words, if a wave is a disturbance that transfer energy through matter without transfer of particles, we say that they are mechanical waves. If a wave is a disturbance that transfer energy through space without transfer of particles, we say they are electromagnetic waves. So based on material medium, waves can be classified as mechanical or electromagnetic waves. We have other classification of waves, and before we even go deep into this classification of waves, let's look at the difference between waves and particles. Take particles to be sand, powder, dust, ball around you. Take them to be particles. And take waves to be vibration in strings, ripple on the surface of water, light itself, X-rays. How are particles different from waves? This will enable you understand waves better. Particle, they occupy a defined space. Now look at it. If this is, okay, let's use a big particle. Let's say dust. If this is a big dust, or let's say chalk, this is a chalk dust, it occupies a space. When you come around, you see that, okay, this chalk is here, or this powder is here, this dust particle is here. They have a defined space. But waves, on the other hand, they don't have a defined space. They spread out. If you watch my video on wave mechanics model, I explained that scientists like Werner Heisenberg, Louis de Broglie, and Schrodinger, even Nebel, later they were able to find out that electrons, they don't just behave as particles, they behave as waves. Why? They are moving so fast that you cannot just say that, okay, this electron must be here. That was why the concept of orbiter was introduced, to give us a possibility, a region in the nucleus where there is possibility of finding electrons. because since they are waves, they can't be in one place. So they don't occupy defined space. You cannot say that this wave is here like this and it must be there. No. So waves, they spread out. Meanwhile, particles, they are in a defined space. You can say, okay, look at that particle there. Let me touch. But it is not true for waves. The second difference between waves and particles is that particles do not interfere. Meanwhile, waves interfere. What is interference? If this particle is here, another particle cannot occupy this same space. They cannot merge together. No. Let me use this as example. If this is here, this one cannot come and still occupy this same space. It can't. So it means it can be closer or far away, but it can't occupy the same space. That is interference. So when one particle is present, another particle cannot be exactly in that position. They do not interfere. But waves interfere. If one wave is here, another wave can still come and occupy that same space. We refer to that as interference. Now, interference can be constructive or destructive. When you have a particle here, another particle here, another one, this total value of the particles is simply adding all the particles. Okay, this particle, this particle, this particle, this particle. You add them. So the sum will give you the total value. But for waves, when waves interfere, if the interference is constructive, they add up, then you get a bigger value of waves. If the interference is destructive, you get a smaller value of waves. Now, energy of particles depend on rest mass, potential energy, and kinetic energy. Rest mass is simply inertial mass. From the first law of motion, Newton's first law of motion, a body at rest will remain at rest. If the body is moving, it will keep moving on that uniform straight line, with uniform motion in a straight line, unless it is acted upon by a force. Now, that refusal of an object to move if it's in one position, or the refusal to stop moving if it's already moving, it is referred to as inertia. So the energy of particles depends on its inertia or rest mass, potential energy. Potential energy is the energy an object possesses due to height. So when you are at a height, your potential energy is simply mgh. Kinetic energy is the energy a body or an object possesses due to motion. So when a body is moving, when there is motion, kinetic energy is present, and it is half mv squared. So the energy of matter depends on the rest mass, potential energy, and kinetic energy, while the energy of waves depends on frequency and amplitude, which you will see very soon. Particles, they possess volume, density, and mass. You can say, okay, this is the mass of this particle, this is the mass of this object. But waves, they have little or no mass. They can just simply be energy, no mass. And examples of particles: a grain of sand, ball, dust, powders. These are particles. You can see them, objects, they have mass. They can come together, they can be big. Meanwhile, for waves, ripples on the surface of water, vibration on strings, light waves, radio signals, and X-rays. These are waves. And don't forget, a wave is a disturbance that transfers energy through matter or space without transfer of particles. This takes us to classification of waves. Classification of waves. Some books will tell you that the types of waves are transverse waves and longitudinal waves. Some will tell you that the classes of waves are mechanical waves and electromagnetic waves, while types are transverse and longitudinal. Some will tell you that the types of waves are stationary and progressive waves. To avoid all these misunderstandings or confusion, waves can be grouped into three based on medium, whether they require a material medium or not, based on direction of movement, What is the direction of movement of the wave to the direction of the particles? Also, based on the ability to spread, is this wave moving about or is this wave on one position? That is what we shall cover right now. Based on medium, waves can be classified into mechanical waves and electromagnetic waves based on whether they require a material medium or not. Material medium refers to as matter or a medium having mass and occupying a space. Mechanical waves are waves that require a material medium, matter, to propagate. They require matter to transfer energy from one point to another. Examples are slinky waves, water waves, and sound waves. You may be wondering, what is slinky waves? Slinky wave is something like this. You see a spring. So this is one end, this is another end, something like spring coiled from one end to the other. So the slinky wave is a mechanical waves. It requires a medium to propagate. Water waves require medium. They require water to propagate. Sound waves. Sound doesn't travel in vacuum or empty space. Sound needs air. It needs metal, non-metal materials around to travel. If you remove air, you remove material medium, when someone is speaking, you'll be unable to hear the person. So sound is a mechanical wave. Then we have the electromagnetic wave. These are waves that can travel in space. They don't need matter to propagate. They don't need a material medium. Their medium is simply the electromagnetic field, which is not a physical or a material medium. And they are simply Gazulia, gamma rays, X-rays, ultraviolet rays, light waves, infrared rays, and radio waves. They are electromagnetic waves. You see electromagnetic spectrum later ahead. Now, do you understand the classification of waves based on medium? Then secondly, if you are writing a theory exam and they ask you what are the classification of waves, you may simply just say mechanical waves and electromagnetic waves depending on what you are taught. But for objective exams and general exams, this should work. Based on direction of movement, waves can be transverse or longitudinal. Look at something. Let this be waves. Let's say the wave is going this way. Let this be medium. Now, what is the direction of the waves to the medium? Is the medium moving in the same direction as the wave, or is the medium moving in perpendicular direction as the wave? That is transverse and longitudinal wave for you. In transverse wave, the medium moves in right angle to the direction of the waves. It moves in right angle to the direction of the propagation of the wave. This is it. This is the wave is going this way generally. You see the medium is going like this. Either like that or like this. Now you see something like this. Right angle or perpendicular means 90 degrees, like this or like this. So which means if this one is going here, this one is going up, coming down, going up, coming down. That is transverse waves for you. Examples of transverse waves are light waves. When you spread the light, you notice that it is moving perpendicular to the direction of the waves. Ripples in pond. If this is pond, you hit here, you notice that the ripples, they spread. So any wave that spread goes up and down, is simply a transverse wave. So when you are given a question, which of these is a transverse wave? Try to look at the options. Which of the waves scatters, like goes up and down, to and fro? That is simply a transverse wave. Guitar strings, when you pluck a guitar strings, you see the waves moving up and down. That is a transverse wave. Stadium waves, when someone scores a goal, Messi! You see everybody in the stadium like doing like this, hailing the player, or people in stadium going up and down. When you look at that wave, you see that it is simply going like this. So that is transverse wave. Goes up, goes down, goes up, goes down. So in definition, we say that the direction of the medium is perpendicular or at right angle to the direction of propagation of the waves. Then S-wave earthquakes. Earthquake can either produce transverse wave or longitudinal wave. For S-wave earthquakes, the direction of the wave is perpendicular or at right angle to the direction of the medium. So it is a transverse wave. In longitudinal waves, the direction of motion is parallel to the direction of propagation. The medium moves to and fro in the direction of the wave. Look at something. If I am here, this is your ear, and I say physics, this is the sound, right? Now this is the air particle. Air particles to your ear. What happens? Physics. By the time I say physics, you see that this particle goes here, it collides with this one. This one collides with this one. This one collides with this one. Now, as this particle hits this one, it comes back to its position. Then this one goes front to hit this one. As this one hits this one comes back. This one goes forward to hit this one. As this one hits this one goes forward. Then this one comes back to its position. So, something like this. These are the air particles. This is the sound wave going this way. Physics. So this particle hits this one, right? It comes back. This one in front goes front to hit this one. After hitting it, it comes back. The other particle hits the other one and come back. Now you see the movement of particles to and fro. Now they are moving to and fro in the direction of the wave. Now they are not going up and down like transverse wave. In transverse wave, you see the waves goes up, comes down, goes up, comes down. But for longitudinal wave, it goes to and fro in the direction of propagation of the sound, or in parallel, move parallel to the propagation of the sound. Now this is what happens. I say physics. This particle moves to hit this one. You notice something. At this point, this particle and this one are very close. This one and this one, they are far. Therefore, the part where the particles are closer is referred to as compression in longitudinal wave. The part where the particles are far apart is referred to as rarefaction. So, let's say, imagine we have many of them. Physics, this hits this one. Then immediately this one hits this one. It comes back to its position. This one goes forward to hit this one. You notice that there is space here. Then these particles are closer together. So that is what happens in longitudinal waves. You see a part where the particles are close together, then a part where you have space. That part where the particles are very close together is the compression part. The part where you have space is the rarefaction. Examples of longitudinal waves are sound waves, like I just explained. Waves in string with one end fixed. If there is a string here and one end is fixed, as you vibrate, you notice that it moves to. It doesn't oscillate because one of the end is fixed. So the movement of the particles is in parallel to the movement of the wave. Then P-type earthquake waves. I told you that earthquake waves can be transverse or longitudinal. The P-type earthquake waves, they are longitudinal, which means the particles move to and fro in the direction of the wave, or the direction of the particles is parallel to the direction of propagation of the waves. Now, the parts of transverse waves are crest and trough. Since transverse waves are moving up and down, or longitudinal, or at right angle the particles are moving at right angle to the direction of the waves, the highest point of the particle is referred to as crest, and the lowest point is referred to as trough. So the parts of transverse waves are crest and troughs. Crest being the highest point, trough being the lowest point. Meanwhile, the parts of longitudinal waves are compression and refraction. Compression, you see, where the particles are more together. Refraction, where there's a little bit of space. So if I ask you, what are the parts of longitudinal waves? You see compression and refraction. What are the parts of transverse wave? Crest, the highest point, and trough being the lowest point. Based on ability to spread, we have stationary or standing wave, then progressive or traveling waves. Stationary waves is a wave that is produced with restriction. For example, if you have a spring or a rope, two people are holding, one person is holding a rope at one end, the other person is holding it at the other end. That wave is produced with restriction. So as this one vibrates to the other end, the other one vibrates to the other end, you discover that there is interference. They interfere. On the other hand, progressive waves, they are produced with no restrictions. The wave spread out. For example, water waves and sound waves, they spread out, no restriction. But for stationary wave, they are produced with restriction. So when two people are holding ends of rope, as this wave goes here, then the wave from the other person comes down. So you have something like this. You have this wave going, another one comes, until you see a situation where the waves, they interfere, they join together like this, they become stationary. The parts of stationary waves are nodes and antinodes. Nodes and antinodes. Nodes and antinodes. The antinode is the highest point, while the node is the lowest point, as you can see here. When it comes to stationary wave, the distance from one node to another, this is the wavelength. Wavelength is simply the one point in a wave to exactly that kind of point in another part. This is what I'm saying. This point here now, the second similar point is here. This point here, the second similar point is here. So from here to here is one wavelength. Time to complete a complete wave. This is a complete wave. So when you make one complete wave, you see that it is one wavelength. So from node to node is simply lambda over 2. From here to here is lambda. So from node to node is simply half of lambda. So lambda over 2. Now this is node, this is antinode, this is node. From antinode to node, you see the small part here. This is simply the wavelength divided by 4. Therefore, the distance from node to node is lambda over 2. The distance from node to antinode is lambda over 4. Take note of that, because this, as well as stationary wave equations, traveling wave equations, will be very, very important for calculation. Wave motion possesses certain properties, and it is different from particle motion. Remember, earlier in this video, I explained or I compared particles and wave. In this case, I will compare wave motion and particle motion. Before then, look at this typical wave. This is the y-axis, this is the s-axis. And here is the direction of propagation of the wave. The wave is moving in this direction. What is happening? You see this up and down here is the direction of vibration of particles. Does this explain a typical transverse wave? Yes. The direction of particles is at right angle, or it's perpendicular to the direction of propagation of the wave. The wave is moving this way, but the particles are going up and down at 90 degrees. Now, this maximum displacement from this rest position is referred to as amplitude A. This is rest 0. It goes up until it gets to maximum. So that maximum point from the mean point or from the rest point is referred to as what? Amplitude. Now, wavelength is lambda. It is the distance from one point in the wave to the exact point in another wave. For example, look at this point in this wave, then look at the exact point in this other wave. So here to here is wavelength, or it is distance from crest to crest. This is the highest point in the wave. C is crest. Trough is the lowest point in the wave. So from this one highest point to another highest point is wavelength, or from one lowest point to another lowest point in the wave is referred to as wavelength. So we have a frequency. Frequency is simply the number of waves per second, number of waves that travel or propagate at every second. That is frequency of wave. Then I explained compression, rarefaction, and other terms associated with waves earlier while classifying waves. Now, wave motion is vibratory or oscillatory. Meanwhile, particle motion can be translational, rotational, oscillatory, or random. Particles of the medium are not carried along. During wave motion, you have a medium, but the particles of the medium, they are not moved along with the wave. The wave, they don't carry particles. But for particle motion, motion has bulk mass. So mass is being carried. Like during breeze, harmattan, you see particles of sand moving up and down. Sawdust, you see the particles jumping up and down. The medium is, particles of the medium are being carried. Then wave motion exhibits interference, which means two waves can exist in one space, but particles don't interfere. Two particles can't exist in exactly one point, like this, exactly like this one cannot enter inside this one. And wave, they have variable acceleration and force, but particle motion, they have constant acceleration and force. So I've explained wave motion. Now, let's see the properties of water waves. The first property of water wave is that it is a mechanical wave. What is mechanical wave? They are waves that require a medium to propagate. In this case, the medium is water, surface of water. They are progressive. This means they spread out, they travel. Their movement isn't restricted. They are transverse wave. This is a typical wave of water. Transverse wave. The direction of propagation of the waves is in right angle or perpendicular or at 90 degrees to direction of vibration of the particle. Wave is going this way, but the particles are jumping up and down at 90 degrees to the direction of the waves. And water wave experiment can be carried using a ripple tank. Let's see the relationship between frequency, wavelength, and speed. We know what frequency is, we know what wavelength is, we know what speed is, velocity of waves. Take note that velocity is equals displacement over time. Velocity is displacement over time. Now, velocity is also, displacement is simply distance traveled in a specified direction. So we can take the wavelength of a wave to be the displacement or the distance traveled, as you can see. So if the wavelength is lambda and t is capital T, which is period. Period is the time taken to complete one oscillation. So from here to here is one oscillation. So what is the time it takes for every one oscillation to complete? That is period. And take a look at something. Period is 1 over f. Period is inversely proportional to frequency, because frequency is the number of oscillation per second, while period is time taken to complete oscillation. So for period, time comes first before oscillation. For frequency, oscillation comes first before time. Therefore, frequency and period are inverse. If this is true, it therefore means that V is equals, from here, 1 over T times lambda. And T is 1 over F, it means that F is equals 1 over T. If period is 1 over frequency, frequency is simply 1 over period. So instead of 1 over period here, we can simply replace it with frequency to have V is equals frequency lambda. So this is the relationship between frequency, the wavelength, and speed. V is equals F lambda. This will make sense to you later. The properties of waves. The properties of waves are reflection, refraction, diffraction, interference, and polarization. I will explain these properties in layman terms so that it will keep ringing in your medulla oblongata. Now, what is reflection? Reflection is simply a phenomenon where waves can bounce off a surface. For example, if you shine this torch on this board, you see it reflects. So sometimes it can reflect on your eye depending on the angle, or it reflects back. Why? The wave is unable to pass through the board, so the surface is bouncing back the light waves. That is reflection. In our day-to-day life, we encounter a lot of reflection. Even on the road, maybe when it's raining or when it stops raining, as you are driving or you are in the car, you see the road reflecting a particular light to your face, which can be referred to as total internal reflection. Now, when the surface is flat, the angle at which the rays bounce on the surface is the same angle at which it leaves the surface. That is referred to as the law of reflection. The incident ray is equals the reflected ray. Now, what is incident ray? This is a torch. I shine it on this surface. So the light coming from the torch or from the source is the incident ray. And the angle at which the light is pointed at the board is the incident angle. So if I'm shining a torch like this, so the torch is coming, this is 3D, but the board is 2D. So we can take it to be this way. So this angle, this is the perpendicular. So this angle is the incident angle. The angle at which the rays is entering the surface. Now, the ray also bounces back. So this is the reflected ray, the ray that goes back. Incident ray is going here, here is being reflected. So the angle at which it is reflected is the angle of reflection. So the law of reflection says that when a light shines on a plane surface, the angle of incidence is equals to the angle of reflection. And reflection is a phenomenon where waves can bounce off a surface. The second property of waves is refraction. Refraction is a phenomenon where waves can bend, and this happens when waves move to a region of different density. For example, you have a glass of water. The water is here. Then you have a straw. You put the straw here. Now, as it enters the water, you notice a bend here. So this is air and this is water. Due to different densities, you see that the wave is being refracted. So it changes direction or it deflects. Then it now appears to bend. You can try it. Put straw in water, half filled, or any particle. As you look, you notice there is a difference in angle. So that is refraction, and it is a property of waves. This is the incident index, this is the refractive index, and this is the incident angle, this is the refracted angle. So you see, as this wave enters another density, which is from air to water, there is a shift in angle, or there is a bend in angle. So that is refraction for you. And refraction obeys Snell's law. Snell's law. Snell's law says that ni sin theta I is equals nr sin theta r, which means incident index times angle of incidence is equals refractive index or refracted index times angle of refraction or refracted angle. So this is the refracted index. This is the incident index. So this is the angle of incidence, angle of refraction. So incident index times the sine of incident angle is equals refracted index times sine angle of refraction. So this is Ni over N arrow is equal sin theta arrow over sin theta I. And don't fail to know that the refractive index of this medium is simply the velocity of in air over velocity in water. So refractive index is the velocity of wave in air over the velocity of wave in water. And if the wave moves from shallow water to deep water, the refractive index will simply be the velocity in the shallow water over speed in the deep water. That is refractive index. And wave can diffract. So another property of wave is diffraction. Diffraction is bending of waves around an object. Example, bending of water waves through narrow openings. Or if I am here and I say, hey, you can hear me, right? Good. Now what if there's a tree here? The tree is covering me. You are at the side of the tree. If I say, hey, will you still hear me? Yes. The wave, they bend to bypass the tree and get to you. That is diffraction. Waves, they bend off objects. Even torch, when you shine a torch at night, due to the dust or particles in front of the torch, you see that the light waves, they are being diffracted, they spread out to get to where they want to get to. So this is another property of wave. Then the next property of wave is interference. Remember, when I was explaining the difference between waves and particles, I said that particles cannot interfere, but waves can interfere. So interference is the overlapping of waves of overlapping or combination of identical waves. You see one wave going, another one overlapping. Now, examples of interference or real life examples are beautiful colors. When you boil soap for a long time, all those beautiful colors you see in soap, they are as a result of interference. Or oil on the road, you see so beautiful color, very beautiful color of oil, drop of oil on the road. That is interference. And interference is different from superposition. Superposition is simply combination of two waves to achieve whatever you want. You simply combine two waves. And look at it. For interference to happen, there are conditions that must be met. One condition for interference is that more than one vibrating source is required. You need more than one vibrating source for interference to take place. And two, the sources must be coherent, which means they must have the same wavelength, the same amplitude, the same phase, or exactly the same phase difference. So the conditions for interference are more than one vibrating source is required. Two, the sources must be coherent, meaning they must have the same wavelength, the same amplitude, and they must be in phase. If they are not in phase, they must have the same phase difference. They must be out of phase by the same angle. That is condition for interference. Polarization, on the other hand, is an exclusive property of transverse wave. So transverse wave, only transverse waves are polarized, and polarization is a restriction of an incident wave into straight lines parallel to a perpendicular direction of vibration. Restriction of an incident wave into straight lines parallel to a particular direction of vibration. Restriction of an incident wave into straight lines parallel to a particular direction of vibration. That is polarization. The stationary wave equation is y equal to a sine 2 pi over t, where a is the amplitude, t is period. Therefore, if you are given amplitude and period, you'll be able to answer questions under stationary wave. But this is not a hot cake topic. This is the boss, progressive waves. When you see questions under waves that require calculation, there is a high chance that it is under progressive wave. Most questions in waves are theoretical questions, and if you watch this video over and over again, like 5 to 10 times, everything should ring in your brain and you should be able to answer questions under waves that don't require calculations. For a progressive wave, the equation is simply y is equal to a sine theta minus phi. This is along s-axis, positive s-axis. Along negative s-axis, this plus changes to minus. But that shouldn't be a problem now. Y is equals a sine theta minus phi along positive s-axis. What is A? A is amplitude. If you are given this wave, the maximum displacement from the position of rest or from mean position is amplitude. Theta is the displacement angle and phi is the phase angle. This can be rewritten as y is equals a sine wt minus ks. Theta is wt and ks is the phase angle. So displacement angle, phase angle, we've not changed anything. What is w? Angular velocity w is equals 2 pi f, like we already know. And what is k? K is 2 pi over lambda. Therefore, the progressive wave equation can be rewritten as y is equals a sine 2 pi ft minus 2 pi over lambda s. You can call this equation 2, equation 3. You can call this equation 1. With these equations, you should be able to solve any question under waves or progressive waves. When you see questions, what do? You compare the wave equation given to the original wave equations. In the process of comparing, you'll be able to find amplitude, frequency, wavelength, velocity, and period. These are the top 5 things you'll be asked under progressive waves. And in this case, I am using one stone to kill all the 5 birds. And any question you see, they are similar. It is left for you to compare. If you see any question under progressive wave and you are unable to answer, send it to me. I will answer it for you. And the second question says, find the distance between the consecutive antinodes if the wavelength is 60 centimeters. I think we should answer this to get rid of it because it is not worth occupying space. This question is piece of cake. I told you that the distance from node to node is lambda over 2. And I told you that the distance from antinode to node is lambda over 4. The distance from antinode to antinode is lambda over 2. In this case, they say we should find the distance between consecutive antinodes given the wavelength to be 60 centimeters. Distance between node is lambda over 2, antinode is lambda over 2. But from node to antinode is lambda over 4, which means if you are looking for node to node, consecutive nodes or consecutive antinode, it is lambda over 2. And this is SS is equals lambda over 2, and this will give you 60 centimeter over 2. That is 30 centimeter. You've answered that question. Is it clear? Yes. Now let's look at this solution. You are given y is equals 4 sine 100 pi t minus 50 pi s. Looking at equation 1, equation 2, and equation 3, which one should we compare with? In this wave, we have pi and we have t. So we should compare with the one that has pi and t. And the one that has pi and t is the same thing as this, just that this one is expanded. W is 2 pi f, k is 2 pi over lambda. So bringing this one here, we have y is equals a sine 2 pi ft minus 2 pi over lambda s. With this, food is ready. How? Comparing this and this, lambda is equals, amplitude is 4. So amplitude is 4. If we are giving it in centimeter, we can say okay, 4 centimeter or meter, whatever. But A is equals 4. Simple, right? That is it. It is easy for you to get amplitude. Now look at this. Sine, minus, minus. Now look at this. Comparing them, it means 100 pi t is equals 2 pi ft. So this and this are the same. Pi t cancels pi and t. So 100 is equals 2f. Dividing both sides by 2, f is equals 50 hertz. Or this can be meter, whatever. So the frequency is 50 hertz. So f is equals 50 hertz. Makes sense to you, right? Good. Now let's compare here and here. So if minus 50 pi s is equals minus 2 pi s over lambda, minus goes with minus. So we are left with 50 pi s is equals 2 pi s over lambda. From here, I can see that pi s can cancel pi s to have 50 is equals 2 over lambda. Lambda is therefore 2 over 50. That is 1 over 25. That will give you 0.04 meter or 4 cm. And please, this is in meter. That's it. Wavelength is 0.04 meter. The next is velocity. What is velocity? From the relationship between velocity, wavelength, and frequency, we establish that V is equals F lambda. This is simply 50 times 0.04. That should give you 2 meters per second. 50 times 0.04 is 2 meters per second. That is the velocity of the wave. And what is period? Period is 1 over frequency. That is 1 over 50. Because frequency is 50. So ladies and gentlemen, we've been able to find the amplitude, frequency, wavelength, velocity, and period of progressive waves. With this, we come to the end of waves. Not the end, but the end of this class. Because there are more videos covering sound waves, light waves, and other parts of waves you need to understand. If you find this class helpful, why not subscribe to this channel? Feel free to let your friends know about Flash Learner's YouTube channel. And don't forget to like or comment. Thank you. Enjoy.